So this series of videos is going to discuss phases and properties of matter, as you can see. So we've talked about some of this a little bit before in the physics section, but we want to talk about it in a little more depth because we're going to be talking about different parts of this as we go through the chemistry section. So a couple of terms I just want to make sure that we get ironed out as we go through these next several chapters. So the first one is compounds. So compounds are substances made up of a combination of elements. So these are going to have properties unique from the elements that are in them. So an example of this would be, for example, what you see here. So we've got sodium metal. So we saw in previous videos that sodium is a very soft metal, and you can see it's dull. It's dull, it's not reflective, and if you remember as well, sodium is one of those metals that's highly reactive to water. So, it's very different from the material that it's going to be making in this compound. We're going to add it to chlorine gas. So chlorine is a gas and, sodium is a solid. So chlorine gas might not be very familiar with. So chlorine gas was actually used in the Second World War as a chemical weapon because chlorine gas is actually deadly to humans. So we've got a explosive metal and a deadly gas, and when they react together, they end up forming sodium chloride, or something that you might know more as table salt. Something that is actually not toxic to us, not really harmful to us, obviously, unless we have it in very high concentrations. And not only that, something that's essential to us. And you can see it's a crystalline structure, so very different structure from the two parent materials, and it is a solid like the metal, but looks nothing like the two parent materials, as well as not having the same properties as the two parent materials. So a compound then is a substance made up of a combination of elements. So then what is a molecule? Because you've probably heard of things being called molecules. So a molecule is the smallest particle of a compound or a gaseous element. So you can say that you've got a molecule of ammonia here. So it is a compound. It's made of nitrogen and hydrogen atoms that are bound together. Or you can have atoms of the same type to make up a gaseous element. So for example, oxygen or nitrogen gas. Hydrogen is another one. So they've got multiple atoms bound together. You can even have technically a molecule of helium, but that's actually just single atoms. So we don't typically call those molecules for the noble gases because those are traveling around as single atoms. Generally, when we talk about molecules, we're talking about two or more atoms joined together, but they are single sets of those atoms in a material. So a gas element or a compound, but it's a single unit of those rather than a big mass of them. So phases of matter, like I said, we looked at this before, but just as a review. So we've got solid. So solid is going to have that definite shape and volume. And why is that? Again, remember those atoms are packed tightly together. And so they're not going to have the ability to move around. And so that's what gives them that definite shape and volume. We've got a liquid state. That's the one with that variable shape, but a fixed volume. So again, the volume is fixed because the molecules can't move very far, but the shape can change because the molecules aren't as tightly packed together as they are in that solid. So they can move, they can flex, but they're still at a fixed volume. So if you compress it, it won't change the shape basically of the container that it's in. It would end up breaking it. And that's due to those looser molecules, those spaces in between the molecules or atoms. And then the last one, my face is over top of it, there we go, is a gas. No fixed shape or volume. And this is because those molecules are far apart from each other, as you can see in the picture here. And they are moving around randomly and colliding in with each other. So we also have very different energy states. So we go from a lower energy state, with these guys packed closely together, to a high energy state, because these guys are moving around randomly and colliding into each other. So which of the phases take up the most volume for any material? That one should be pretty easy to figure out, and that is the gas form. And that's because those molecules space out from each other because they have those higher energy states. They're bouncing around, and so they need that bigger space. And so a great way to see this is with something like dry ice. So dry ice is frozen carbon dioxide. There are some places around where you can purchase this if you want to give it a try. Do be careful if you do, because this is cold enough to actually create burns on your fingers due to the cold temperature. And so what you can do is break it apart. And in this case, as you can see in the demonstration, they're putting some of it in a balloon and then sealing that balloon up, sealing the container, and then allowing that frozen carbon dioxide to warm up, because the room temperature is much, much warmer than the freezing point of dry ice. In fact, it's above the point at which it turns into a gas. So it actually turns pretty much immediately from that solid to a gas. And so that balloon will expand very quickly after you put that in. So the next thing I want to talk about is diffusion, because this is related to material states. So diffusion is the tendency of molecules to move from an area of high concentration to low concentration. So pretty much all molecules want to do this. They want to move to where there's a lot of them to where there are very few of them. So if I grab my pen here, so it's the same idea as people, right? We don't like to be in very big, tight crowds. And so you can imagine all of these dots as molecules or as people. And so as they move around, they're going to space apart, because as they bump and move around, they're going to want to get farther apart from each other. And you've probably noticed this at places where there are crowds. When we can, we try and space ourselves out farther and farther apart. And so this is the idea of diffusion. Area of high concentration and move towards areas of low concentration. Okay. So what are some examples of this? Well, you've actually experienced a lot of them. And this picture is a great example of that. Odors are going to travel by diffusion. This is why it can take a while for a good smell or a bad smell to reach you. So a good example of this around my house, I have a cat. I don't know how many of you might have a cat, but when the cat uses its litter box, I don't immediately smell it, but after a couple of minutes or so, I start to smell it and need to go take care of it. So this is a much more pleasant version of that. You know, when you start to bake, for example, one of my favorite things is to bake brownies. And so when that process starts of baking the brownies, you don't smell it right away, but after a while, that smell starts to move throughout the house. And that's the idea of that chocolate kind of smell is concentrated right there by the oven, but over time, the molecules from the brownies start to spread out across your apartment or your home, and then eventually those molecules reach you. So turn my pen off. The thing is that all of the phases can do this. So you can see that actually here with the liquid phase. So they're putting in food coloring and you can see it doing that. It's staying concentrated, but then over time it spreads out more and more and starts to color the beaker more and more. You've probably experienced this with things like tea or Kool-Aid. I especially notice it with my tea when I make tea, like hot tea. The tea color stays pretty concentrated right around the tea ball until I move it, and then it starts to spread out. If I just let it sit there, it eventually would spread out on its own, but it just takes time. But all of the phases can do this. So solid, liquid, gas, all can do diffusion. So which one, though, do you think can do it the fastest? And if you said gas, yeah, that makes sense, right? Because those molecules are moving the fastest. And so diffusion happens the fastest with gases, then liquids, and then solids are going to diffuse the slowest. But solids can diffuse. It just takes them a very, very long time to do it. All right, so let's take a look at phase change. So how does it happen? You guys are actually pretty familiar with this. So if we go first, we're going to look at solid to liquid. So if we go from solid to liquid, you know that as melting, right? And if we go liquid to solid, freezing. Right? When these processes happen, though, there's actually energy involved, and we'll see that on our next slide. When we go in the different directions, in one direction, we're going to gain energy, and in the other direction, we're going to lose energy. Then, if we're going liquid to gas, this one, again, you're pretty familiar with. If we're going liquid to gas, we're evaporating. So we're going into that gas form, into the gas phase, that's evaporating that liquid off. If we're going from gas to liquid, we're going to condense. So the most common one that you're probably familiar with as far as condensation is like if you have a cold cup or something like that sitting there, it's condensing the water out of the atmosphere because it's colder there on the cup on the outside. And so you're cooling down the molecules and they're getting attracted and stuck to the cup. The one that people aren't as familiar with probably is the solid gas one. And we call the one where we go from solid to gas sublimation. So this would be, for example, the dry ice example. So when we go from the solid block of dry ice to the gas form, if we just let it sit, if you've ever seen I'm sorry, my brain stopped for a second. If you've ever noticed your ice cubes in your freezer slowly disappearing, that's actually sublimation. What's happening is that your freezer is slowly converting the solid ice cubes into gas vapor. And so they are actually kind of melting, they're sublimating. Then you've got deposition, that's the other direction. Sometimes people actually call this sublimation as well for both directions. So when we go from a gas to a solid directly, and the most common way that you've seen this happen is actually still in the freezer. If you open the freezer and you see those big chunks of like frost around the edge, that is gas to solid because the water vapor from the air has frozen into the solid immediately. It didn't go through the liquid phase. It went straight to that solid phase. The other example I can think of off the top of my head, because there's not a lot of solid gas examples that are common, but the other solid gas one that you may have run across, especially if you work in like the fiber arts or something like that, would be mothballs, because mothballs do the solid gas. That's actually where the scent of them comes from. The naphthalene does that solid gas sublimation. So let's take a look at the energy part of the phase change. So I told you that we lose energy in one direction, gain energy in the other, and hopefully it makes sense that as we go from solid to liquid to gas, that's how we gain energy, or we add heat. So you add heat to get the phases to change in that direction. That also means that we add energy, or we gain energy. So heat added, energy gained. Okay, so on this direction, the molecules are going to be gaining energy because remember, thermal energy, heat, same thing. And so the molecules are gaining more and more energy, which is how they're being able to go from the solid to the liquid and then eventually to that energetic gas. The opposite's happening when we go from gas to liquid and then liquid to solid. The heat is being removed. Those molecules are losing their energy.